This video will cover section 9.7 probability. The objectives for this section are to find the probabilities of events, to find the probabilities of mutually exclusive events, and also to find the probabilities of independent events. So we will be discussing the difference between those, the ones that are mutually exclusive and the ones that are independent, and of course the ones that are dependent. And then lastly, to find the probability of the complement of an event. And so we will be defining that in a minute, but just so you know, a complement is the probability of the complement of an event is the event that the probability of that certain event will not happen. So the negation of it, for example. Any happening for which the result is uncertain is called an experiment. And the possible results of the experiment is what we call the outcomes. The set of all possible outcomes together, it is referred to as the sample space. So each individual possibility is an outcome, and the set of all of those is the sample space of the experiment. Any subcollection of the sample space is an event. And so an event will be a subset of the sample space, and it could be one outcome or more than one outcomes, but with something in common. For instance, when you toss a six-sided die, the numbers 1 through 6 can represent the sample space. For this experiment, each of the outcomes is equally likely to happen. So a fair six-sided die with the numbers 1 through 6, those are, each number individually is one outcome, and the collection of all of them is the sample space. And for example, to describe sample spaces in such a way that each outcome is equally likely, you must sometimes distinguish between or among various outcomes in ways that appear artificial. So in this case, and I say the word fair so that each number has the equal probability to land, and so we call that equally likely outcomes, and the probability for each of them is equal. Since you have 6 outcomes in total, then the probability to land on each number will be 1 over 6, but we will do more examples of that. To calculate the probability of an event, count the number of outcomes in the event and in the sample space. So going back to the previous slide, if the question was, what is the probability of landing on that the six-sided die it lands on a 3, then it will be 1 over 6 because there is only one way to land in a 3, and the total of the outcomes is 6. So there's one way to get a 3 and total 6. If the question was, for example, was the probability of getting a 2, it will also be 1 over 6. So the number of outcomes in an event, for event we will use the letter uppercase E, and the number of outcomes of such event is going to be denoted by N of E. So N lowercase for number of. And the number of outcomes in the sample space, it will be denoted by N for number of S. And of course, sample space, we will use S for that. So if I go back here, the set of the sample space, that will be capital S. And for example, here, number 1 is representing the number of ways to get a number 3. And the 6 is representing the number of the sample space. So that would be N of S, which is 6. Okay, So we could find any probability simply by dividing n of e, the number of events that are of the same, then, and then divided by n of s, which is the number of outcomes in the sample space. So you can look at it, the same division. We have it listed here or here. And then for the number of outcomes of certain event, n of e, that will always be on the numerator. So it is like a fraction where you are always going to divide the part over the whole thing. So in this case, the whole thing will be the collection of all the outcomes for the sample space, and the part will be the number of outcomes for a certain event. Going back to the example that I have here, if the question was, what is the probability of getting an even number out of 1 through 6? And so even numbers, we have 2, 4, and 6. So the number of events to get an even number will be divided by the number of events of the sample space. And so that will be there are 3 even numbers out of 6. And of course, we always want to reduce or simplify the fraction. So this will be 1 over 2. Because the number of outcomes in an event must be less than or equal to the number of outcomes in the sample space. So you cannot have more events than the total of events of outcomes in the sample space. The probability of an event must be a number between 0 and 1. So I know sometimes you might hear things like there's a 30% chance of rain, but in reality that 30% is representing 0.30 or 30 over 100, or simply we could say 0.3. So that probability of 0.3, it does satisfy the condition that it must be from 0 to 1. So if we 0.3, it will be like somewhere maybe here, 0.3. And if we were to convert 0.5, probability of 0.5 to a percent, 0.5 to a percent, it will be equal to 50%. And for example, 0.25, that will be 25%. So the 30% chance is, of course, bigger than 25, but lower than 50%. And 1.0, which is the total number of, I guess, let's just call it 100%. And that will be the maximum number that you can get for the probability of an event occurring if that event was the whole sample set. So for example, if the question, going back to the rolling a die, it's what is the probability to get a number less than 7? So if you look at the sample set here, all numbers are less than 7. So in this case, the n of that certain event, less than 7, divided by the number of elements in the sample space or outcomes, will be 6 out of 6, which it will be 1. And a probability of 1 is, of course, that you're certain that it will happen at any time that you roll the die. So going back to translating this into words, 0.0 probability will be that the event is impossible, or the event will simply not occur because it just cannot occur. Probability of 0.5, it means that, of course, is just as likely as it is unlikely. And you might hear the very common phrase 50-50 because there is 50% chance that it will occur and 50% chance that it will not occur. And then if we have a 1, like rolling a number smaller than 7, then that will be a certain that the event will occur. So probability of events, we use P, capital P for probability, and then P of E for the probability of a certain event. So if you ever have, going back to that diagram, a probability of 0, the event cannot occur, and if it is a 1, the event is a certain event. So let's go ahead and work with example 2. So we have you toss 2 coins. What is the probability that both land heads up? So each coin has 2 sides, and let's say the first coin could be heads or tails, and the second coin, it could be as well heads or tails. But if we combine both events, meaning that we could toss both coins at the same time or one before then the other, we will have 4 different combinations. And those combinations are listed here. So we could get for the first and for the second coin, actually I'm going to use numbers here. So first and second. So we could get heads on the first, heads on the first, on the second, or we could get heads on the first and then tails on the second. Then we could also have tails on the first and heads on the second, or tails on the first and tails on the second. So from there is where we get those 4 pairs that you see here on the sample space. So the probability, the question here is what is the probability that both land heads up? And you can see that within the sample space, there is only one way that that could occur, and that is 1 out of 4 events in the sample space. So the probability that you will obtain heads on both coins, then it will be the number of the occurrences for that event, which is only 1. This is the only way. And the number of the sample space is A4. So let's look at the next problem, and that talks about something else. So I want to give you guys an extra question here. So if I was to ask you, what is the probability to get at least a 1 tail? So, and this looks like a G. Okay, so probability that you could get at least 1 tail. So I'm going to highlight every single event that has at least 1 tail. So here we have 1, and you might think, well, we have 2, but the word is at least. So that means that we could have 1 or more than 1. And of course, here with 2 coins, the maximum will be 2. So this one will still count. Then we have heads on the first, tails on the second, and then we finally have tails on the first, heads on the second. So we have 3 of those events. It could be heads, 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 tails, tail, heads. So that will be 3 over 4. Now, if the question was only 1 tail, oh, and I actually highlighted the wrong ones. So it should have been heads, tails, tails, heads, and then tails, tails. Sorry about that. So yes, just so that it matches the question. So those will be the 3 outcomes, but it's still 3. So now if we say only 1 tail, then we're not going to consider the one at the end of the sample space. So it will only be the 2 in the middle, heads, tails, or tails, heads. And so for that one, the probability of obtaining only one tail will be 2 over 4, and simplified it will be 1 over 2, so 1/2. If whoever sign wants the answer as a decimal, please be very careful with that. Don't enter fractions if they want a decimal, and don't enter decimals if they want the exact answer. You have to leave it as an integer or a fraction. So 1/4 is equivalent to 0.25, and then we have here 3/4, that's equivalent to 0.75, and of course we have 1/2 is equal to 0.5. So please be careful when you do your homework. Now, still with example 2, but this is a different problem. You draw one card at random from a standard deck of playing cards. What is the probability that it is an ace? Because there are 52 cards in a standard deck of playing cards, and there are 4 aces, 1 in each suit, the probability of drawing an ace is. And for those of you who are not familiar, and we should have done a problem with yesterday's topic. So I think I'm going to go back and revise that. So, but just so you know, in a deck of cards, a standard one, you have these things called suits. And that will be the symbol that your card will have. So those will be hearts, diamonds, clubs, and spades. So from those suits, of course, we have 2 cards that are red, or 2 suits that are red, and then the other 2 are black. Now for each suit, you have a total of 13 cards. So those 13 cards will be the ace, and then the numbers 1, no, not 1, I'm sorry, that will be the ace. 2, from 2 to 10. 2 to 10. And then we have the jack, the queen, and the king. So that gives you your 13 cards. And that is true for every single suit. So there's an ace of diamonds, there's an ace of hearts, an ace of clubs, an ace of spades. For diamonds, of course, same thing, 2 to 10. Then we have jack, queen, and king. And the same repeats here. So I'm just going to do that. So what they're saying here is that, well, if you add 13 plus 13 plus 13 plus 13, or 13 times 4, you do get 52. So that is the total number of cards. So the probability of drawing an ace, since they are 4 aces, as we already discussed, then it will be 4 out of 52. And of course, we always have to reduce our fractions. So if we divide 4 by 4 is a 1, and 52 divided by 4 is a 13. So that would be the probability of drawing an ace. Now, what I want to discuss is something from 9.6. And so there was a problem on the textbook, and I didn't realize it wasn't on the PowerPoint, so I want to go over that now. So the problem says, and how many different hands of poker can you get when you have 5 cards chosen out of 52? And if we do this, it will be a combination, so it will be 52 factorial over 52 minus 5 factorial, and then 5 factorial. So this will be something like 52 factorial over, and 52 minus 5 will be 47. So 47, and then 5 factorial. So if we enter this on the calculator, we will get 2,598,960. those are the total number of hands of poker that you could get. So, for example, to get certain hands, there are different probabilities. And by the way, getting four of a kind, it's not the highest that you could get. There is a thing called a royal flush, and that one is the more unlikely to happen, and therefore is the one that has more value because the probability is way smaller. The probability of getting two pairs or one pair is greater than any others. So that's why it's the lowest price. So let's talk about mutually exclusive events. So two events, A and B, from the same sample space are mutually exclusive when A and B have no outcomes in common. So mutually exclusive, no outcomes in common. In the terminology of sets, the intersection of A and B is the empty set, which implies that the probability is zero. So let's go over this for a second. So let's say that we have the deck of of cards, 52 cards. So the probability of drawing a red card and the probability of drawing a black card, those two are they have nothing in common because all cards are either red, diamonds and hearts, or they're black, clubs and spades. And so that's a perfect example of a mutually exclusive of two mutually exclusive events. So since the intersection, and you could think of a Venn diagram, we could have here, this will be the set of all red cards and the set of all black cards. And of course, here within the red cards, we have all the hearts within in the diamonds. And over here, we have the clubs and the spades. And so they have nothing in common, so there's no intersection. A set with an intersection will look like that, and whatever is considered here in the middle overlapping or that belongs to both sets, that is what we call the intersection. So for example, if this was all my aces, and here I had the ace of hearts, and these are all my cards that are hearts. Well, there is one that belongs to both sets. It is a heart and it is also an ace. So that will be not mutually exclusive, but the ones where the intersection is the empty sets, such as the A intersected with B, is the empty set. Just two, well, those are very ugly curly brackets, like that. Or we could also use the symbol for empty set. That is the empty set, not zero. So the intersection is the empty set, meaning they have nothing in common, literally just the curly brackets without, like, empty with nothing inside them. So the probability of the intersection, that is zero, and this is not the empty set, that's the actual number zero, because remember, probabilities run from 0 to 1. And so if the intersection is empty, then the probability of the intersection is empty, and that takes us back to mutually exclusive. So for instance, when you toss two dice, the event A of rolling a total of 6 and the event B of rolling a total of 9 are mutually exclusive. So the events of you getting a total, and here we're considering two dice, so it could be like getting a 1 and a 5, or a 2 and a 4, or a 3 and a 3. And I mean, if we don't consider order, of course, it could be like a 4 and a 2, a 5 and a 1. And in the event of rolling a 9, that will only be obtaining a 3 and a 6. Um, uh, yes, that will be the only one. Or obtaining a 6 and a 3 if you don't if you care about the order of the first and the second dice. So those are mutually exclusive. You can see that they have no outcomes in common. So of course, mutually exclusive, just like drawing a red card and a black card from a standard deck of cards. So going to the next slide, we have mutually exclusive events. To find the probability that one or the other of two mutually exclusive events will occur, you simply add their individual probabilities. And this is for mutually exclusive. Once they're not mutually exclusive, then we have to do something to subtract the intersection. So let's go over mutually exclusive first. So we simply add the probability of one plus the probability of the other. And here what it means is the probability of A or the probability of B occurring. In probability, we relate the symbol for union to the word or, and we use addition. So for intersection, and I'll just write it down here. So for an intersection, A intersected with B, it's going to be the probability of A times the probability of B. And in words, we say this, the probability of A occurring and the probability of B occurring. So we relate the symbol here for intersection to the operation of multiplication and to the word and. So that is mutually exclusive. So when they are not mutually exclusive, such as the example that I have here of drawing an ace, and one set is all the hearts, the other set is all the aces. So there is one in common. And so if we were to find the probability of getting a heart from a deck of cards, it will be 13, because there are 13 hearts out of 52. And the probability of getting an ace, it will be 4 over 52. So out of those two probabilities, we have one out of this 13 and out of this 4 that they have in common. And of course, that's the one that I have here in the intersection. That will be the one that is both a heart and an ace. And so how many of those do we have? We only have 1/4. 1/4. So if we were to go to this problem and find what is the probability of getting a heart, and or an ace, remember this union means or, then we will have to find the probability of getting a heart. So we wouldn't just simply add them, because if we add the 13 over 52 with the 4 over 52, we will be counting, we will have an extra one. So that will be wrong, and that is because they are not mutually exclusive. So going back to the right way to do the problem, we have the probability of getting a heart from a deck of cards plus the probability of getting an ace. and then minus the probability of getting one that is both a heart and an ace. And that's the one that in the Venn diagram, the one with the two circles, looks like it's highlighted with yellow. So the probability of getting hearts, we already said it was going to be 13 over 52. The probability of getting an ace was going to be 4 over 52. And the probability of getting both, a card that is both a heart and an ace, will be only 1 out of 52. So in this case, we will have 13 plus 4, that's 17, minus 1, that is 16 over 52. And if we simplify this, we will get 4 over 13. And so that will be the question of a heart or an ace. But because they are not mutually exclusive, we have to do subtract the intersection so that we don't count that one card twice, the ace of hearts. So next slide, we have here example 8, and it talks about the human resources department of a company has compiled data showing the number of years of service for each employee, and the table shows the results. So you could see on the left column, we have the number of years of service. So people within the 0 to 4 years of service, the number of those people in that category is 157. People who have been there from 5 to 9 years, there are 89 in total. This is the number of, and so on. So you could see that we have some people here, for example, 25 to 29, that would be 38. So for each number, like time period of service, that will be those will be considered the categories. And I know that both of those are numbers, but that is the categories. And then the one on the right is the number of actual employees. So you can see here at the bottom, we have 2 people who have been with the company for 45 years or more. So good for them. So we have the first question here. What is the probability that an employee chosen at random has 4 or fewer years of service? So let's see. 4 or fewer will be the same as 4 or less. And for that question, we need the category from 0 to 4 years. And the number of those employees is 157. So we need N of E. The event is that they have 0 to 4 years, and that is 157. Also, we need the total number on the sample space. And so for that, we will have to add all the employees that we have on the right side column. So if we add them, the total of those is 529. So then we will have this problem, 157 divided by 129. So with web assigned, be careful. They might want the exact answer, or they might want a decimal representation. 157 and 159, they have no factors in common, so we cannot reduce the fraction, so that will be the exact answer. Now, if my math lab wants a probability, which is very common to have probabilities as decimals, then you will have to approximate according to what they want. So I'm trying to get an approximation with my calculator, and this is approximately 0.2968786. That's how many digits I'm seeing on my calculator. But make sure you read how far they want you to round. So, for example, if this was to the nearest, let's say to the nearest, let's say they wanted 8 digits. I'm not 8 digits, I'm sorry, 4 digits after the decimal point. So then um, 4 digits, but then you still need to look at the 5th digit and see what that will do to the 4th digit. So if that 5th digit is higher than 5, it will cause the 4th digit to turn into, to go up by 1. And so in this case, it will be 0.2968. And that will be the answer. So just be careful on how you round. And we have another question from the same set of from the same sample space. So it says, what is the probability that an employee chosen at random has 9 or fewer years of service? So if we look at the data, we have the category here. The second category has 9 or fewer, which is from 5 to 9. And then, but we also have the first category, which is from 0 to 4. So these two categories happen to be mutually exclusive because you cannot be at work for 1 year and also for 5 years. So they are, the categories or the two events are mutually exclusive. So to answer a question that implies or, we simply have to add. So we're going to be adding 157 plus 89. Okay, so I'm trying to understand this question because I don't think this answer is correct. So I'm going to check with the textbook. To me, the question that has 9 or fewer years of service should include definitely the ones who are from the 5 to 9. Or 0 to 4, because that, to me, that is fewer than 9. However, the PowerPoint is telling us to only consider the ones from 5 to 9. I don't really agree with this. And you could see it is 89. But I feel like the question should have been worded, what is the probability that the employee chosen at random and has 9 or fewer, but 5 or more. So to me, that's what the answer here, 89 over 529, that should be the answer to this question. Well, I'm gonna make my own question. So if the question was the probability that an employee has 9 or less years working there, so then it will be the 157 from this category 0 to 4 over 529 plus the 89 over 529. So if we calculate that, it will be 157 plus 89, which is equal to 246 divided by 529. And that gives us approximately 0.465. For the one that we have here, if it was, to me, it's like 5, between 5 and 9. That would be even a nicer way to say it. Between 5 and 9 years of service, that would be 89 out of the 529 total employees. So that would be approximately 0.1682 for 2. Okay, so oh, okay. So all we had to do was look at the next slide. So yes, I was right about the question, but I did not know how they were gonna work it out. But the exact same thing that we did on the slide is here. So here is the probability of the category 0 to 4, which we already have. 157 is what we have here. And then the event B was the probability from 5 to 9. Okay, so yes, I'm sorry. And here we have the union, so remember that is OR. So the probability that the people are in the 0 to 4 or the 5 to 9. And so it's the same result here, 89 over that. And then if we add that, we get the 246, same thing that we got here. And that is approximately 0.465. So now let's move on to independent events. 2 events are independent events when the occurrence of one has no effect on the occurrence of the other. For instance, rolling a total of 12 with 2 6-sided dice has no effect on the outcome of future rolls of the dice. Or you could think of tossing 2 coins. Whether you get heads or tails on your first coin, it has nothing to do, it will not influence the other outcome of your second coin. So to find the probability that 2 independent events will occur, multiply the probabilities of each. And actually, yeah, I want to go back and correct that over here. I was probably doing this too fast because when things are, this will be for an independent event, like the slide that we're on. And if they were, for example, dependent, such as this one, we don't multiply the probabilities. You could just simply count how many of those there would be. And so if the question was here, what is the probability of getting a heart? And that is also an ace, then that will be simply 1 out of 52. So they wouldn't be they will not be a need to multiply these 2 probabilities because we could just easily identify which one is both. So the statement that we have here, which is the same one that I had mentioned previously, will be true only for independent events, such as what is the probability of getting a head on the first coin and heads on the second coin. So if we say probability of getting heads and heads, and we know they're different coins. This is the first coin and this is the second coin. We're tossing them like maybe at the same time. The outcome of one doesn't affect the other. So this will be 1 out of 4. But we could also find it by calculating the probability of getting of the coin landing on heads for the first coin, and not plus, Tommy, stop. I'm sorry, times the probability of getting heads on the second coin. And so the first one, it is 1 out of 2 because remember it's 50-50 heads or tails, and the second one is also 1 over 2. So if we multiply that, we get 1 out of 4. So we have some questions here with example 9, and this is the probability of independent events. So we have a random number generator on a computer, selects 3 integers from 1 to 20. What is the probability that all three numbers are less or equal to 5. So all three numbers. So the event, and we denote A, is going to stand for all three numbers are, or no, not all three, or one single event will be to obtain a number that is less than or equal to 5. So how many numbers are from 1, 2, 3, 4, and 5, and 6, and all the way to 20? So the only numbers that will satisfy that condition will be 1, 2, 3, 4, and also 5, because we have the word equal. If it said less than 5, we will stop at 4, but we have equal. So how many out of those? 5. 5 numbers are less than 5 or equal to 5. Out of how many? Remember the number of the sample space, so that's 20. Now, if we simplify this fraction, 5 divided by 5 is a 1, 20 divided by 5 is a 4. So that is the probability of obtaining a number that is less or equal to 5. Now, if we want all three of those numbers that are generated randomly with a computer, that we will have to do a multiplication. So for each one of those, we have 1/4, as you can see here. So the probability that you get a number in that category is 1/4, and that you get it again is also 1/4, and that you get it again is also 1/4. Or I think I said it 4 times, but only 3 times because we have 3 numbers. So if we multiply all of that, remember we must multiply straight across horizontally. So 1 over 4 times 4 times 4 is 64. And so that will be the answer in exact form. If it is approximation with decimals required, make sure you divide 1 over 64 and that you round accordingly to the question. Now let's talk about complement, the complement of an event. So the complement of an event, let's call the event A. So the complement of event A is the collection of all outcomes in the sample space that are not in A. So that is what we connect the complement with, not in A. So since probability goes from 0 to 1, and let's pretend that the probability for A is right here at 0.2, for example. So the probability of event A is 0.2. So the probability that event A will not occur, it's going to be whatever is not in the 0.2, but it's still part of that 1 of the total. And so you could find this by subtracting 1 minus 0.2, and that will give you 0.8. And so we denote this, the complement, you could see here with with an apostrophe there. You could also call it a complement, but you can also call it, and we have it here, complement of A. That's what it will be. But you could also, some people refer to it as A naught. So the subtraction that we did here, it will be the same as saying 1 minus the probability of A. And that is how we find the complement of certain event. So that you have the formula here. The probability to find the probability of the complement of A will be always 1, which is the total, minus the probability of certain event actually occurring. So if we were to add the probability of event A plus the probability of not A, then it will always give us 1. So since I made this up and I say the probability of A is 0.2, so if we add 0.2 or 0.2 plus 0.8, we will get 1. So for instance, if the probability of winning a certain game is 1/4, then the probability of losing the game is going to be 1 minus 1/4. And of course, 1 needs to be converted to fourths, so it will be 4/4 minus 1/4, so it will be 3/4. So it is easier or more likely that you will lose than that you will win this game. So just in general, always 1 minus the probability of that certain event. So we have example 11, and it says a manufacturer has determined that a machine averages 1 faulty unit for every 1,000 it produces. So one unit for every 1,000. What is the probability that an order of 200 units will have 1 or more faulty units? So here we want to take the sample space, the number of units in the sample space are 1,000, and we get the number of the, let's call E will be the defective. The event E will be the defective units, and so that will be a 1, right? 1 out of 1,000. So the probability of getting a defective unit, it is 1 out of 1,000. Or in decimal form, this will be 1.0001. No, sorry, it's 2 zeros and then the 1. And so 0.001, that's what it will be, the probability. So the question here is talking about getting a subset of 200 units or an order of only 200 units. And so we want to find the probability that it within those 200 units, that 1 unit out of the 1,000, we will find the probability that 1 single unit is within that order of 200 units. Okay, so going back to the previous slide, this will be the probability of getting exactly 1 defective unit. So I should put here 1 defective unit only. But the question, it says 1 or more faulty units. So if we read the next paragraph here, it says that to solve the problem as it is stated, we will need to find the probability of having 1 defective unit or the probability of having 2 defective units or the probability of having 3 defective units and so on, all the way to the probability of having all defective units. That will be very small, but it could still be a possibility. So the only event that negates the obtaining 1 or more faulty units will be the event of obtaining no faulty units. And so the probability of obtaining no faulty units is actually this fraction subtracted from 1. It will be and it will be 9. Of course, if we subtract 1 minus 1 over 1,000, this will be 1,000 over 1,000 minus 1 over 1,000. and this will give me 999 over 1,000. And so that will be the only way that you will not get a defective unit. So it will be kind of like the opposite of of obtaining one or more. So the event of obtaining no faulty units will be 999 over 1,000. But since we have this and we want to have this with 200 units, so it makes sense that we multiply that 900 over 1,000 because we want to be that. And so it will be all of them, like the first unit, the second unit, all of them, all the way to the last unit, which will be the 200th unit. We want it to also be non-defective. So we have a good chance of that. But so to calculate how many times we will have to multiply, we have to consider how many units we're talking about, and we're talking about 200 units. So we will be multiplying that fraction by itself another 199 times, or 200 times total. So it's the same as using the exponent of 200. And so if you enter this on your calculator, make sure you do enter in parentheses 999 over 1,000. You can close your parentheses and then use the exponent symbol 200, and that's how you will come to this decimal. And so that will be the probability that all of your units will be okay. They will not be faulty. So if we want to find, remember that was P of A, no faulty units. All 200 cases or 200 units had the probability of not being faulty. But the question of the problem was, what is the probability that at least one of them? So, and that means 1 or 2 or 3 or all the way to 100. That's why it was easier to use the complement of the obtaining no faulty units. So that will be 1 minus 0.819. And so if we subtract that, and you need to keep in mind that this could be only one faulty unit, or 2 faulty units, or 3 or 4 or 5 or 6 or 10 or 20, or even all of them, 200. So that will be a small number, and this will be 0.181. So that at least one of them will be faulty. It is a small number, but since we only have 200 units, it is a bigger number that at least one of them will be defective, bigger than the fact that out of 1,000, one will be defective. So probability is very interesting if you have to take a statistics class. This will probably be like the first day of class, but you will learn very interesting things. And if you do go into certain fields of engineering or science, you have to take a more advanced, perhaps a probability class. I know electrical engineers have to take that. And you learn more of it, but I wish we had more sections on it because it is interesting and it's also pretty easy to do. So this is the end of the video.